Alright, I'm back. Oops, hold on, I didn't do this. Gotta kill the music. All of you people eating better than the instructor. I mean, I'm old and will die soon, so you have so much to live for, so you should be eating healthy. What was I going to click on before I actually did anything? I don't remember. I'm all over the place today, I guess. It's what happens when you wake up and fall back asleep and you're like, oh no! Now I only have an hour to do everything I need to before lecture. So, let's see. Announcements for this week. I sent out an announcement last night at like 3 a.m., realizing, oh crap, I never told the class what I wanted to do this week. So hopefully you've read the announcement. It is mostly regarding Wednesday. As a little bit of inside information on the lab that you're going to do this week, it basically needs no introduction because it's kind of like a lab final in the sense that I'm really just kind of asking you to do stuff from previous labs. It's the wine lab, and so if we were actually in person doing the wine lab, what we would do is I would hand you a sample of synthesized wine, so either Chardonnay or Riesling, and I'd say, tell me what's in here, good luck, and that's it. Like, that would be the entire lab introduction. So more or less, that's what I'm going to do tomorrow, and that's kind of a waste to have you come out for just 1 minute. So I'm going to tack on an extra lecture tomorrow, so if you can make it to tomorrow's lab lecture, I'll still be able to answer questions if you have them. But I will also keep lecturing on Chapter 4 stuff so that we can get as much of it done. Chapter 5 is actually like an hour. So if we get to Tuesday next week and we haven't started Chapter 5, then we're good, because Chapter 5 takes like one lecture, because it's so short. I don't know why the book does that. But Chapters 3 and 4 are just really long, and I want to make sure I get through all of Chapter 3 and 4, because they're very important. Other relevant stuff for this week, Chapter 3's quiz is due on Thursday. Make sure that you do that by the deadline. I know people have been asking questions about one of the problems with units. I believe that I have fixed that. If you see something that looks like a really weird frequency, like with a 10 to the minus 19 or 18 exponent or something like that, and you're like, that can't be Hertz, then that issue didn't get fixed, but it should have. Let me know if you see a weird test question, and I'll just omit it for your test sample. But I believe that it should be working now. I do make typos from time to time because I am trying to copy and paste 3 or 4 problems, and then I don't catch all of the things when I update them. So I apologize for that. But let me know how that goes. The quiz for Chapter 4 will be actually the last quiz. There is no quiz for Chapter 5. It's just going to get rolled into the final exam because it's just too short. I didn't think about that when I was making all the content. So quiz 4 will be the last quiz. And then there's exam 2 on Monday. Same deal as last exam, where you have all day to do it. You could do it twice, but it's open at midnight and it closes at midnight. And you have to do it sometime on Monday. I don't care when you do it. I believe the final exam... I haven't read through the syllabus that I wrote. I believe I did something similar for the final exam, but I might have restricted the time more. I might be a little more lax on that just because I know that I have students that are currently in different countries and different time zones taking this class. And to have it open for 2 hours only, or 4 hours, I guess, would really be inconvenient if they had to get up at 2 a.m. So I'm going to try to accommodate that. So don't worry about what the syllabus says for the final exam just yet, because that might change. But I will probably do the same thing I've been doing with the exams, which is just to leave it open for a whole day. That's everything that I can think of that came to mind. So without further ado, if there aren't any other questions, which you can of course type in the chat, which is hiding over here, we're going to do Lewis symbols today. Lewis symbols are probably the easiest thing in chemistry, really. You're just going to draw a bunch of dots, and you're going to look at this and be like, oh man, why did we do all of that electron configuration if we're going to reduce it down to, oh, just pick the group it's in, because electron config is useful for other stuff. But it does kind of show you that how far we've come when we can take all of Chapter 3 that we've learned and then reduce it down to, oh, it's the group number. And that's what we're going to do for most of the day, is we're going to draw Lewis structures all day. I'm going to show you how to draw the Lewis structure for any molecule using a strategy. which you'll want to always follow. If you don't follow the strategy, you get the wrong structure. And we're going to look for patterns. Most molecules tend to follow a certain pattern, but there are some exceptions that we will talk about as we come upon them. And then probably on Wednesday and Thursday, we'll get to geometry and shape and polarity. All right, so let's get started. This is G.N. Lewis. G.N. Lewis did not go insane, as far as I'm aware, like Pauling did. Instead, what he did was he wrote weird pictograms in his book. But these weren't just scrawlings of a madman. These are actually him trying to figure out how the heck are electrons arranged around molecules. And the way that he did this... Oops, that's not my pen. The way that he did this is he had this kind of like cubic shape, and he would put the electrons on corners of this cube. And his idea was that if I combined any two things together and I could fill all of the corners of the cube, I would make a molecule that bonds in some way. So his example here was NaCl. So Na would be this one right here, and it has 1 dot. Cl would be this one, and it has 7. And if I took this 1 from sodium and these 7, right, so I put the 1 from sodium here. If I can do this, then I can create a compound. In other words, oops, I don't know what the C is for. If I can get 8 electrons around an atom, that tends to be stable. And that ends up being very, very important for us, because we saw earlier that things that have 8 valence electrons are stable because they end up with something like this. And we said earlier that if your electron configuration has a full S and P subshell, then the ion or atom that you form is stable. So G.N. Lewis devised what was eventually going to be called the Lewis symbol. And later on, what chemists did was they said, well, we don't need to draw it as a cube. We could just draw it as a picture. Just write the symbol and then just start putting dots around it, where you have... Those are supposed to be circles, but they ended up looking like electrons. You have the 8 positions on 4 sides of the atom. Now, obviously, this is in 2 dimensions, so we're going to use up, down, left, and right as the sides. So we have 8 spaces for electrons to go. And so that's the premise behind the Lewis symbol. Drawing a Lewis symbol is as simple as doing these 2 steps. Draw the chemical symbol of the element you want, and then start drawing dots around it, 1 dot per valence electron on each of the 4 sides. And remember, we only want valence electrons here, and so that's going to be any electrons that are in the highest n. So to start, we're going to draw out the electron configuration and count the valence electrons, and then we're going to find a pattern related to the group number. So here's sodium, and I've already written its electron configuration out here, and I've apparently marked the slide here. This is its valence shell. N equals 3 is the highest level N in sodium, so there is 1 valence electron. So to draw its Lewis symbol, we're going to do the following. First, draw its atomic symbol. There you go. Then we're going to draw a dot for each valence electron. We said that there was 1, so I'm going to put 1 dot. Boop. And there you go. That's the symbol. That's all you have to do. Now, if this were an in-class test, I would just make you draw these. Obviously, I can't make you draw Lewis structures on Canvas. Like, there is not a way for me to make you upload a picture. And also, I think that that's an accessibility issue. I don't know how everybody would do that unless you, like, photographed it from your phone. And I can't make the assumption that everybody has a mobile device. So, it's not really practical for me to have you do that. Even, like, drawing it just in Paint or whatever. But I can still ask you questions about this. Like, how many electrons did you draw? Or how many are paired? Or how many are unpaired? Or things like that. So, we're going to use these symbols to explain bonding. Let's do another one. So let's do oxygen. And what I want you to do is draw the Lewis symbol for oxygen before I reveal the answer. I'll give you the first obvious step, which is you got to figure out the valence electrons. So write out the electron configuration, count the number of valence electrons, and then start drawing dots around your oxygen and see what you get. I'll give you 2 minutes to do that. And we'll go over the answer in just a second while I eat more toast. All right, hopefully you've drawn the Lewis structure. I actually turned around to find my toast, and I had already eaten it all. So I went and got my phone, and my phone alerted me that today is a science fair, and I'm very sad about that because there is no science fair because of the COVID outbreak. Everett CC puts on a science fair every year where we do little demos, and normally what I would have done is I would have asked you guys to do the demos for my students. Or not my students, I'm sorry, but for the 5th graders that we invite to the campus. But everybody is at home, so we didn't get to do that. So you can just imagine that we did science all day instead of going to lecture, which would have been more fun. Oh. Hopefully you wrote down this for the electron configuration. I mean, by now, we should know how to do these pretty much just right off the cuff. If you look at the highest n equals 2 in oxygen, so you find all the electrons that are in n equals 2. And that's these guys. They're in blue. There are 6 total electrons there, so I'm going to draw the symbol. Boop. There you go. There's our O. And then I'm going to draw a dot for each valence electron. So the way that this is going to work is that there's only 4 sides available, and electrons don't like to be next to each other because they repel. So the proper way to do this is to put an electron on each side until you don't have any more sides. And then you start pairing them. Doot, 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 doot. And now I do have to pair them, so I'm going to put my electrons in to the spaces next to other electrons. Doot, doot. Now, if you didn't draw your oxygen exactly this way, perhaps you drew it this way. So 1, 2, 3, 4, 5, 6, maybe. Or even this way. All of these are correct. All that matters is that the number of unpaireds and the number of paireds are the same in your structure versus mine. So in oxygen, I should have 2 paired sets. And then I should have 2 unpaired. And you will always get the right answer if you just put 1 dot down first and then start pairing them. The wrong way to do this would be to do this. So you'll notice that this arrangement has them all paired. But electrons repel, so this one's going to go, oh, I have space over here. I don't need to pair unless I have to. So make sure that you are drawing these correctly by putting 1 dot down at a time and then putting the second dot down. If you put them all down at once, you might think that this one that I've drawn down here is correct, and it's not. And it's, in fact, the only incorrect one. So what I want you to do is draw the Lewis symbol for all of these. Put the letter down, put down a dot for each valence electron. You might have to consider the number of valence electrons by writing out the electron configuration, or maybe you're noticing the pattern of how I figure out how many there are without actually doing the electron configuration. Then down here, some of these have charges on them. I didn't mean to put an extra line there. How do charges change the number of valence electrons? Well, you should know that too, because you know how to change the electron configuration. So be mindful of these charges when you are doing the electron configuration. So we'll go over the answers in about 3 minutes or so. See you in a bit. All right, just a few minutes or a few seconds more to finish up. We'll go over the answers. And we'll definitely touch on, like, can you have zero valence electrons? Well, we'll see. All right, I should have enough space to do this here, so what I'm going to do is I'm going to quickly write out the electron configurations for some of these. And counting the number of valence electrons, we can see that in carbon there are 4, and you should get something that looks like this. 1 dot on each side. I change the color of the pen. So lithium is not that. What am I doing? There we go. There's its valence shell. There's 1 valence electron. Now, excuse me, with lithium, you got to be kind of careful because you don't want to accidentally interpret the dot on the I as a valence electron. So I just make my valence electron really big and obnoxious when I do it for lithium, which is very rare. You won't see lithium used very much. Sulfur, where are we on the periodic table for that? So sulfur is not that pen. Sulfur is neon, 3s2, 3p4. Has 6 valence electrons, and so we would do 1, 2, 3, 4, and then any 2 can be paired, just like that. Now you might have started to notice that, depending on what column you're in, that's going to be the number of valence electrons that you have. So you might have noticed that carbon is in group 4a, and lithium's in 1a, and sulfur is in 6a, and wouldn't you know it? Look at this. Now, if you have the other designation for groups, then what that looks like is this. So you might have noticed, oh, carbon's in 14, lithium's in 1, and sulfur's in 16. You just get rid of the tens digit, and it's all fine. So you just use the ones digit, and that's the number of valence electrons. So now we don't even have to use electron configurations. I can just say, chlorine is in group 7a, and so it has 7 valence electrons. So chlorine's Lewis structure must look like this. There you go. And again, that single unpaired can be on any side as long as the other 3 are paired. Aluminum is in group 3A or 13, so it's got 3 valence electrons. 1, 2, 3. There you go. That's an extra electron here. There you go. So B+, boron's in group 3. So it should have 3 valence electrons. But we made it positive. And when you make things positive, you remove electrons from them. So this actually only has 2 electrons. So I'm just going to draw 2 electrons. Excuse me. But I also am going to do one extra change, and that is that I'm going to put brackets around it and put a charge on it to indicate, hey, this is an ion. Whenever you have an ion, you'll want to put square brackets around your structure. And this is just a convention. I didn't tell you this on purpose so that when you didn't do it, you'd be like, oh, I have to do that. Maybe you did do it because you read it in the textbook, then that'd be great. For Br minus here, it's in group 7a, so 7 valence electrons. But we got this minus here, and when you have a minus charge, it means you've added extra electrons. So same deal as before. We would put down all of our valence electrons, put brackets around it, and put the charge in the top corner. Xenon's an 8A, so it has 8 valence electrons. So here's xenon 1, 2, 3, 4, 5, 6, 7, 8. Now, there was a question I was asked, can you have 0 valence electrons? And the answer is only if you are H+, and you have all the electrons removed. Of course, that could be for like an alpha particle for helium or something, which has no electrons. But generally speaking, H+ is common enough, and helium alpha particles are not. Because there will always be a valence layer. If I looked at my carbon up here and I got rid of all of these guys, then now these are the valence layer. So there will always be some valence electrons. So saying that there's 0 isn't technically true. So it's always better to just say 8. Later on, we're actually going to try to reduce things down to, quote, 0. And when we do that, we're going to just work on the assumption that there are 8 valence electrons when we discern the octet rule. All right, that's how you draw Lewis symbols, so let's keep going. Now, our goal for making ionic compounds is not just to match up the charges like we were doing before. We're going to show how this actually happens at the electronic level. And so whenever I make ionic compounds, I will react them in their elemental form by moving around electrons. Now, I don't remember if I showed you Lonnie's lab. Did we see Lonnie's lab? Lonnie is the creepy guy, where he makes salt. We did see this. Okay, so I'm not really sure why this is in my slides a second time. But just to remind you that when we do ionic bonding, we transfer electrons from the element that is the metal to the element that is the non-metal. Yeah, he eats the boiled egg in the lab, which is just like, Lonnie, what is wrong with you? There's literally chlorine gas right next to you. Don't eat eggs. That's just a general rule for life. Don't eat eggs around chlorine gas. In fact, be as far away from chlorine gas as you can. Now, the way that this works is that when we move our electrons around, we're going to move them so that everything has a full S&P subshell, like we said before in Chapter 3. But visually speaking, we can just show this as, oh, I'm going to just slide this electron over here. Oops. And now I have 2 different ions, each of which has a full octet. And the way that we're going to show this is by writing out the octets. And that's the wrong end of the pen. That's why I can't see my cursor. So for chlorine here, we've got neon 3s2, 3p. Nope. There we go. 3s2, 3p5. I don't know why I didn't select there. Which if I add this electron in here, it's going to go in this space. Now it's going to become 3s2, 3p6. And I have a complete S&P subshell, so this is stable. For sodium over here, I have, and I'm going to write out the whole electron configuration. You'll see why in a second. When I move my electron, I choose to move the valence electron. It's the easiest one to move. And when I do that, now, whoop, there's my full S&P subshell. So the previous layer becomes the octet that we're looking for. You're going to hear me say that word before I actually introduce it, octet. When you have 8 valence electrons in the S and P subshells, it's formally called an octet. So by moving my electrons in this way, we can make our ionic compound where everything achieves a full S and P subshell, and the resulting compound is more stable than it was in its elemental form. And I believe that... Oh, we don't show that on this slide. Okay, so you saw it on this slide here, and there you go. All right. Now, when you form ionic bonds, you have to make ions first out of your elemental atoms. And then the act of making those ions causes the ionic bond to form. So, if I have my charges here that have formed after I have passed over electrons, now these two are attracted to each other. Typically speaking, we're only going to form ionic bonds between metals and nonmetals. However, you can substitute out polyatomic ions for those. Either side. So instead of a metal, you could use ammonium. Instead of a nonmetal, you could use phosphate or carbonate or any of the negatively charged anions. The same principle applies. It's just that when you take the polyatomic ion, all of the shuffling of electrons has already occurred. All right, so using Lewis structures, what I want you to do is shuffle electrons around and try and make these compounds. So, for instance, I'll show you this one right here, the third one. What we're going to do is we're going to take these two atoms and move electrons around so that we can give everybody a full S and P subshell. Oh, I keep selecting the wrong pen, sorry. So first, let's count the number of valence electrons in Cl because I already have that color selected. There I go. And then for magnesium, I should only have 2. And so what I'm going to do is I'm going to move electrons. I'm going to get rid of this electron right here, and we'll pass it over to chlorine. And so this chlorine would then have 8 electrons because it's got one of magnesium's. This magnesium, however, still has an extra electron to pass over. So what that means is that I need to give it to another atom in order to do this. So if I have another Cl available for me to pass electrons to, then I can do that. This one has an octet because it's got a full S and P subshell. This has removed all its electrons from its valence shell, so the layer below it becomes the octet. And then I would say, okay, well, what's the compound? MgCl2. I used 1 magnesium and 2 chlorines. So this is what I want you to do. I want you to shuffle your electrons around to try and find the ionic bonds. And when we get back, I will show you the answers to these two. The first two are pretty straightforward. So go ahead and try these. I'll give you a few minutes to push electrons around, and then we'll go over the answers, and then we'll move on to covalent bonding. All right, 1 or 2 more minutes. All right, where is... Here we go. So let's do this. So I'm going to show you the bottom 2 because I think the top 2 are pretty self-explanatory. You get KBR and CaO. Let me do this though. So I want to do this one right here. So let's do sodium in black. And then I'll do nitrogen in red because that's what's selected. All right. I'm drawing my electrons kind of as little like hoops or circles just to make them bigger. All right, so I'm going to pass an electron over to here. So this guy's good, but I'm going to need to do that multiple times, as you can probably see. And if I do that 3 times, then I would pair this guy and this guy and this guy, and I'd be all set. So the formula must be Na3N. All right, let's do the next one here. Gotta do this with aluminum now. Oops, I didn't put the dots down. And oxygen. So each aluminum is going to be able to pass over 2. So this oxygen is now satisfied. But I have an extra electron on aluminum, so I need to do that like this. Grab another oxygen and pass over my electron. Now this aluminum is good, but this oxygen does not have all the electrons it needs, so it needs another aluminum. Which means I got to get 3 more electrons. And you can see where this is going. When does it end? And the answer is it ends right here. So we can do that, and we can do that. This one's good, and this one's good. So our compound is Al2O3. So we did this in a very similar way when we were doing electron configurations, but now we can do it graphically, and we don't have to worry about electron configurations anymore. I mean, not until the final. Or exam 2. Okay, you do have to worry about it, I guess. All right. Let me know if there's any questions. We're going to now talk a little bit about covalent bonds before the break, so you can at least see how they work. And then when we come back from the break, we will do the draw a Lewis structure for anything rules. So First, let's talk about what covalent compounds look like at the valence structure level. And that is that if I were to draw something for, say, fluorine here, and I were to pair it with sodium, then this would be really easy. I would just put this here and we'd be done. But if I put fluorine with another fluorine instead, if I do this sort of thing, this one's satisfied, but this one is actually further away. I want to get 8 valence electrons, and doing this action means that I now have 6 instead of 7, so that's worse. And so that's not going to happen here. So nothing on the screen is good. We'll just get rid of it. Now, elements with really high electronegativity don't pass their electrons onto other things, unless it is to something that has even higher electronegativity. Fluorine is as high as it gets, so fluorine's never going to give up its electrons. So how do we get there to be 8 on both of these and make F2, which is how fluorine gas exists? And the answer is, we do this. I'll let you see that again real quick. It took me an hour to animate this, by the way. And the reason it took me an hour is because no matter what I did, I could not get these 2 electrons to line up perfectly, which is super frustrating for me. So now you can unsee it. Thanks, Wes. All right. What I have done here, though, is if I look at the number of electrons around fluorine on the left, it looks like I have 8 valence electrons. And if I do the same thing on the right here, oh, look at that. It looks like we have 8 valence electrons. And you'll notice that I put it in quotes because I sort of double counted these. But in reality, these atoms don't know that because they don't have brains. They're just matter. So atoms are dumb and they don't realize, oh, I can have 8 valence electrons. We can both have 8. As long as we share. And so this is what happens. Whenever you put 2 electrons between 2 atoms, they will share the electrons between themselves and form a bond. And this is how covalent bonds occur. The nucleus is positively charged on both ends, and in the middle is going to be the electrons that will stabilize that. We usually redraw this so that we don't have just 2 dots hanging out in the middle, because dots are kind of cumbersome to look at. And we end up needing the space to connect other atoms when we draw larger structures. So we'll just pull these apart. Now, ionic bonds are not the same because they are transferring electrons. When sodium gives its electron to fluorine, sodium loses it and it's gone. And then when that happens, I misdotted that. Once this has happened, now the bond forms between the ions. So this is my ionic bond. And this right here, yes, this is F2. This bond right here is the result of sharing electrons. And if I were to unshare them, I would end up with 2 individual fluorine atoms, and not an F plus and an F minus. Now, whenever you share electrons, we represent that with a line. Each line represents 2 bonded electrons. And my line is a little bit crappy, so I guess we'll get rid of that. Around the outside of my atoms, I will have pairs of electrons that are not bonds. These are called non-bonding electrons. In our Lewis structures, what we're going to be doing is we are going to be drawing structures that will have 8 valence electrons. And the reason for that is because they want to have full s and p subshells, just like we said before. This is true for covalent compounds as well. It's just that the electrons that we put in the shared orbital are going to be double counted. So fluorine has a full 2s and 2p subshell on the left and also on the right, because that last electron that they each pitched in gets double counted for both of them. Therefore, when we're looking at these structures, we don't want to worry about electron configurations anymore. We just want to do it really quickly and say, hey, do we have enough valence electrons to get to that state, which would be 8. And so you're going to count all your non-bonding electrons and then your bonding electrons. And the bonding electrons count as 2 for both sides, because they're shared. Every time you draw a line, it's 2 electrons. If you draw 2 lines, it would be 4 electrons. If you drew 20 lines, it'd be 40 electrons. And what I mean by that is within the entire structure. You could theoretically put more lines between atoms, and we're going to talk about that in just a second. Let's see here. Yeah, let's just formalize the octet rule here. So, again, since we're trying to get 8 valence electrons around each ion or atom, depending on whether we're ionic or covalent, we can summarize this as just, okay, if I want a full s and p subshell, that is 8 valence electrons. Let's just look for 8s. And this is called the octet rule. So the octet rule says that anything that involves ionic bonding or covalent bonding that is in groups 1 through 8a, these compounds tend to form enough bonds so that there are 8 valence electrons. Now, this is a guideline. It is not an absolute truth. We are going to find places later on that break the octet rule for various reasons. But for the most part, atoms want to have 8 valence electrons. There will be some specific cases where they don't, and we will explore those when we get to the exceptions later on today. So ionic bonding is really straightforward. It always follows the octet rule. You just pass electrons around until they get to 8. Covalent bonding is where all of the interesting stuff is, because it does all sorts of unique things depending on the atoms that are used. So for the rest of the period, we're going to talk about covalent bonding and use this notion of I can share electrons to construct Lewis structures for simple molecules. And so we'll do these simple molecules first, then we'll take our break. Let's show the Lewis structures for CF4 and H2O, which are just going to appear on the screen here in a second. So I'm just going to do these on this pad here. Oh no! Oh no! I didn't hit the new layer. Wow, wow, wow. Okay, hold on. Boop. Oh, no, that's not what I wanted. That's not what I wanted. There we go. Control-Shift-N. New layer. Draw on this layer. Alright, everything is good. Alright, now the way to do this is basically connect the dots. And we're going to find out that this method works, but it's really cumbersome. And what I should have done is I should have just done this. So how do we know which one goes in the middle? The one that goes in the middle is always written first, unless it's H. H cannot go in the middle. And the reason for that is because the more electronegative atoms go on the outside, and the less electronegative atoms go in the middle, and we always write the elements in order of electronegativity when we write formulas, with some very specific exceptions. For my CH4 here, I'm going to put my carbon in the middle, because it was written first. Oh, shoot, it's a CF4. Let's just fix that really quickly. Womp womp. That's an easy fix, though. Alright. And you'll notice that I'm putting in the valence electrons the wrong way. I should be doing one on each side, but I'm doing it really quickly. And now what we want to do is we want to share electrons. So I need an electron on this one and this one, so if I share them, I make a bond, and now they all have octets. I can share these guys, I can share these guys, and I can share these guys. So that would be my Lewis structure for CF4. I just connect the dots. Any electrons that are unpaired can then be linked together to form a bond. Because remember, the bonds represent pairs of electrons. For water, I can do the same thing with hydrogen here. I can go whoop, whoop, and there you go, there's water. Now you might notice that water only needs 2 electrons from the bond. And that's because... Let me just write down the term for this. This is because hydrogen only has n equals 1 available for it to put electrons into. So if it can get to look like this, it's satisfied that it has what we would call, quote-unquote, an octet. In reality, hydrogen and helium are only really able to get 2 electrons, because that's how many electrons are in the first period and the first n level. So hydrogen follows what's called the duet rule. All other elements tend to follow the octet rule, except for the really, really light ones like hydrogen and helium and maybe lithium. Everything that we're going to work with that isn't hydrogen is going to follow the octet rule. All right. So there's what our structure should look like when we make Lewis structures out of these. Now, these are really simple molecules, and what that means is that when we draw the Lewis structures, doing connect the dots is fine. But in reality, if I give you a more complicated molecule, this gets really cumbersome very quickly, especially when the possibility of multiple bonds comes up. So that's just talking about the duet rule, which we just talked about. What we need is a better approach than just connect the dots, because if I just gave you a bunch of pieces and said connect the dots, the odds are you won't get the right structure without a lot of hints. And if I could give you a method that gets you the correct structure every time, then that would be really good. And guess what? That's what we have. So when we come back from the break, we're going to talk about multiple bonds real quick. I'll just show you the picture of what we're going to do here. How would I connect these guys so that we can give everyone octet? Oh, I don't know. I guess you'll have to think about it over the break. So I don't have the timer up. Oh, yes, I do. It's right there. Aha. No, that's not what I want. I want this one. We'll tell everybody it's break. So I'll turn on the timer. I'll start the music back up again. And we'll see you in 10 minutes after the break. Alright, sorry about that. Let me turn that off. They are pressure washing the outside of the building, and my window is open, and they couldn't wash my house, or apartment. So I had to go fix that. Otherwise, my living room would be flooded, and that would be bad. Oops, what did I just do? Oh, I did that, okay. Alright, so going back to our discussion on what do we do in this situation, can I fix everything? And the answer is, well, yeah, if I was pairing one electron before to make a bond to satisfy the octet, why not both? Por qué no los dos? And sure, there we go. So if I do this, then what I end up with is something that looks like that. Now, instead of sharing 2 electrons to make one bond, I'm sharing 4 electrons to make 2 bonds. And the result would be a double bond. So we can make as many bonds as I want to, although obviously since 8 is our target, the highest number of bonds you're going to get is 4. So if you make a double bond, you're going to share 2 pairs of 2 electrons, which is 4 electrons. I could also do a triple bond with nitrogen. So for example, here's nitrogen. And I could share these like so, which would actually look like this when it was tidied up. And so this would be a oops, that's not what I meant to do. This would be a triple bond. Now, it turns out that if I try and do the same thing with, say, carbon over here, I have an issue. And the issue is that I can do this like before, but when I try and make this bond happen, I don't have really anywhere to connect to because I'd have to go through the nucleus. The electrons that are on opposite sides can't connect to each other in any real meaningful way. So the number of bonds that we can make between 2 atoms is actually capped at a triple bond. I cannot make a 4th bond using these electrons because these electrons are pointed in a different orientation. And later on, when we get to the end of Chapter 4, and also a little bit into Chapter 5, we're actually going to see that in action when we talk about hybridization. So we're only able to have 3 bonds between any 2 atoms, but you still need to make 4 bonds at most to things. So what that means is that I could maybe connect this to like an H or an F or maybe even another C, like however I want to do this. And the structure can keep going and going and going, and you can get these ridiculously large molecules. But at any point between any 2 atoms in that molecule, the number of bonds that you can have connecting 2 individual atoms is at most 3. Alright. Now, because of these abilities to make multiple bonds between atoms, it becomes really, really difficult to figure out the correct structure for molecules that are bigger than, say, a few atoms. And so what we're going to do is we're going to give you a 5-step plan that shows you, in a flowchart method sort of style, how to create the Lewis structure for anything you'll see in this class and for almost all Lewis structures entirely. Pardon me, I have to just drink my water here. So here's our 5-step plan to draw the Lewis structure for anything. I'm going to give you a molecule, and the molecule that I'm going to give you for our demonstration here, we're going to use CO2. And so let me go here and clear everything. All right. And we'll do that. There we go. All right, so the first step that we're going to do is we're going to count valence electrons. For any molecule that you were given, the first step that you always need to do is to tell yourself how many valence electrons are available for bonding. because valence electrons are going to be both the dots that you put around the atoms and the electrons that go into the bonds that are shared between atoms. So you need to know how many of those are available from all of the different atoms that you have in the molecule. So because I have CO2, what that means is I can look at each of these atoms individually and then just add their valence electrons together. So how many valence electrons does carbon give you? Well, you know its electron configuration, and you know that now we could just go to the periodic table and look at what group it's in. So how many valence electrons does carbon give you? And then how many valence electrons does oxygen give you? And then add them all together. So if you add them all together, type in the chat how many valence electrons I should have total for CO2. And while you do that, I'm going to drink more water, and then I'll write it on the screen. Excellent. We can all do basic addition. And believe it or not, this is actually the part of drawing a Lewis structure where a lot of people will mess up. And that's because counting is hard. And I'm not saying that sarcastically. If I screw up a Lewis structure, it's this part. Like, I'll do like 2 times 6 equals 16 or something silly. So we got 2 times 6 is 12 plus 14, or plus, there you go. Plus 4 is 16. And wouldn't you know it, I'm drawing on the wrong damn layer again. Oh, I'm apparently hitting the button to delete the layer. Okay, well, hold on. I must have reconfigured something. I apologize for all the snafus here, so... Oh, new layer. Layer 1. I didn't mean to do that. There we go. Yeah, I'm using a Wacom, but I'm also in Photoshop, and I'm using the delete key on my keyboard, but I didn't have everything selected, which is why it was just deleting the entire layer to begin with. Because Photoshop. I need layers because I don't want to erase and see the transparency garbo at the bottom. Because I don't know how to select stuff. What is... Oh, right, I have to do this. There we go. I like my tablet. I'm just really... 1, I'm clumsy. 2, my desk setup is not great. And 3, Photoshop. Alright, so we said that this had 4. This was 2 times 6, which is 16. Alright, so now we know the total number of valence electrons that we have in our structure, which is 16. So the next step is that we had to use these electrons to make what our basic skeleton will be for the molecule. And so I call this the framework. Now, when you draw your framework, you're going to put the central atom in the center of all of your other things based on what the formula tells you. In this case, we have CO2, and what that means is that we wrote the C first because it's the least electronegative. So we're going to put it in the center for that reason. Everything else is more electronegative than it, so what those atoms are going to do is they're going to pull the electrons away from the atom that is less electronegative. So this is going to be our basic structure here, and I'll just put it over here. We're going to say C is in the middle, and I'm just going to put the O's wherever I want to. Since there's 2 of them, I might as well just put them opposite. But you could put them diagonal or however you want to for now. We're not going to care about geometry until the end of Chapter 4. Now what we got to do is we got to connect these. So I'm going to go like this. 1, 2. Now that I've connected my atoms together, With bonds, I have to pay for those electrons. Each bond that I drew was 2 electrons, and I drew 2 of them, so I have to take away 4 electrons. So I have 12 electrons left for bonding now. So that's step 2. On the slides, there is a little bit of information that tries to help you. Sometimes, like, the molecular formula is written in order, but in reality, what I have drawn on the Photoshop window right here in red is the reason that we want to, or not the reason, is the methodology by which we want to construct our Lewis structure. We want to put the less electronegative atom in the center and the most electronegative atoms on the outside. Alright, so let me move this window really quickly. Alright, step 3 is to use any of your electrons that are available to distribute around the outermost atoms of the structure first. And you want to give them octets. Now, the reason for this is because the outermost atoms have a higher electronegativity. And so they want electrons before the less electronegative atoms do. So I have 12 electrons available, so what I'm going to do is I'm going to start with one atom and give it all the electrons that it needs before moving on to the next one. So 1, 2, 3, 4, 5, 6. Doing that gives me 6 valence electrons plus the 2 that are bonding for a total of 8. So this atom has an octet. But that cost me 6 electrons. Now I gotta do the same thing over here. 1, 2, 3, 4, 5, 6. I have 6 that are non-bonding, and then the 2 that are bonding from before. That gives me 8, so this one's good. But they used up all my electrons. My C is naked. Yes, it is. My carbon doesn't get anything. It's sad. So now what do I do? What's the next step then if I ran out of electrons? Well, we have step 4 here for other molecules. If you have leftover electrons, you put them on the central atom. Now, this is going to lead to an exception in some cases. If you have more electrons available than you have, than you need for an octet, you still put them on the central atom. And we'll see what that means when we talk about exceptions later. So I could go above an octet in certain cases. But the last step is going to be important for this circumstance right here, and we need to do this to show it. If you get in a situation where you've run out of electrons... I got a pop-up that said my stream disconnected. So you might just get an issue in a second there. Are we back live? Can everybody hear or see me? I froze for a second. Okay, yeah. My screen popped up. I've never seen that before. I bet my internet just kind of like popped out of existence for a second. Okay, sorry about that. Anyway, what I was saying is that if you get in a situation where you run out of electrons and there's nothing that you can do because there's no more electrons put down, then it's time to just share more of them. And the way that we do that is we would say, okay, I'm going to take these 2 and I'm going to put them in this bond. And when I do that, I would then create this bond and erase these electrons because they have then moved. Now, the benefit of doing that is that this oxygen over here still has 8 valence electrons, because it got 4 unpaired, and now it's got 2 bonds for 4 total. So that's 8. But this carbon in the middle has less... it's less naked, I guess we'll say. Since that's what we were saying before. This carbon now is closer to 8 valence electrons. If your screen is fuzzy, go down. There should be something like a little gear icon right here or so. Oh, further down. It's on the window when you hover over it. If you click on that and it says where it says auto 240p or whatever, set that to like 1080p and it will get better. Anyway, to get my octet for carbon, I obviously need to do that again. So I'm going to take these guys and move them into the bond to make a double bond. And now this has an octet. So that's our 5-step plan. Step 1, count your valence electrons. Step 2, draw your skeleton. Set up the framework there. Step 3, electrons on outer atoms first. Step 4, electrons on the central atom last. Step 5, make multiple bonds if you absolutely have to. Step 6, profit. Yeah, there you go. Now, you have to do the steps in that order specifically. So make sure that you don't skip over the steps or go back or do something weird. Carbon starts with 4 electrons. Carbon needs to have an octet just like everybody else. Remember, everybody wants to get to an octet. And each line counts as 2 electrons. Alright, so let's do another molecule here. Let's see here. Oh, yeah, there is one last thing to mention here. So we'll go back to this slide to show this. Down here, this last step is very useful to consider. If at any point you attain a structure that has all of the electrons are used up and everything has an octet, then stop. So you can do this as early as step 2. But if you get to step 3 and you realize, oh, everything has an octet, I don't need to do any more steps, don't do steps 4 or 5. You don't need to. Alright, let's do another really... Oh, this is just CO2. So we've already done this, so this is just walking through how we got to the answer. Alright, let's do another one. Let's do ammonia here. And so my answer will just pop up right there, but let's show how we got to that answer. Why isn't my cursor appearing? Oh, because I have the highlighter selected and I just can't see it. Alright, so I have NH3. First I got to count the valence electrons on NH3. N gives you 5 because it's in group 5A. There are 3 hydrogens and each is worth 1. So I have 8 electrons to work with. I'm going to put the element that's in the middle, or I'm sorry, the element that's written first in the middle. We'll just do this. I'm going to connect them all. Which cost me 6 electrons. I'm going to put electrons on the outermost atoms first, but that's hydrogen. Hydrogen follows the duet rule, and it's already got its bonds here, so it's fine. Which means I'm going to put the remaining electrons on the central atom. That uses these up. There is no need for additional bonds because everyone has an octet, and so our structure is done. You'll notice that mine looks a little more Y-shaped than the T-shaped one I drew in the Molecule Maker program I have. That is totally okay for now. Okay. Alright. I want to do one more of these before I turn you loose to just draw these Lewis structures. I'm going to pick carbonate right here to do a demonstration with, just because what do you do with ions? Well, we already know what you do with ions, right? When I'm counting the total number of valence electrons, I have to consider the ion in there too. If I make something more negative by a charge of 2, that's the same as adding 2 electrons. So those 2 electrons will get added to our total count. So that means that I have 24, I think. 18, 22, 24, yeah. And then, now we just do the same thing. So I'm going to make my skeleton. I've got 3 oxygens, so I'm going to put them all around the outside. I will connect all of them. That costs me 6, so 24 minus 6 is 18. Next step was to put electrons around the outside. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've used all of them. This atom's fine, this atom's fine, this atom's fine. Carbon is sad and lonely. So I need to put any remaining on the central atom. I don't have any left over. So I need to take some of my electrons and make them into an extra bond. Now carbon is happy. The structure is done. But because it's an ion, we got to put it in brackets and put the charge on the corner. All right, let me erase these check marks here, just in case you're wondering what these are. But that is the general process. So what I want you to do is do this for SO3, NH4, PCl3, the chloride ion, and NO+. Okay. Draw the Lewis structures on your paper. Follow the 5-step plan. Make sure that you are using the 5 steps in that order. We'll go over the answers in just a bit. All right, just a few more minutes. Mostly because I'm running out of time and I want to cover the exceptions to the Octet Rule today, and then we'll call it a day. So 1 more minute. Go ahead and finish. All right, so let's see here. Okay, that shouldn't delete the layer this time. All right. Just a heads up. So these marks right here that are on these are supposed to be bullet marks and not like charges or anything. The charges are after. So just be mindful of that. All right, so let's do SO3 real quick. If you drew SO3, you might have noticed, well, I have options on where I can put my double bond. What should I do? And the answer is, for now, any of them. It's fine. Tomorrow, we'll learn about what you need to do in those cases. But if you count the valence electrons, this is 6. There are 3 oxygens, and they each have 6. So this should be 24. So that's step 1. Step 2, make our framework 2, 4, 6. Step 3, atoms on the outside get electrons first. 12, 13, 14, 15, 16, 17, 18. Out of electrons. Doo-doo. Obviously, I need some sort of electrons in the center here, so I'm going to erase these 2 guys on top. And we'll just do this. And there you go, you're all set. So this would be SO3. We already did carbonate. Interestingly enough, you might notice that SO3 had 24 electrons. Carbonate... Oh, I messed up how I wanted to write this. Also has 24 electrons, and it basically looked like this guy did up here, except I just did that to it, right? Interesting. I wonder if there's a reason for that. It turns out, yeah, if you get a certain number of electrons, you're always going to get a certain shape. So when you've done this for a long time, I know what the shapes are just based on the numbers. So whenever I see 24, I just know, oh, I'm going to make a triangle out of it. Because I've been doing this for 10 years. You guys have been doing this for about 10 minutes, so it's totally okay that you don't have the same shapes that I am drawing at the start, and that's okay. Let's do PCl3. We'll just do that. So there are 3 chlorines. Each chlorine is 7. Plus 5 is 26. And in this case, I actually had to not draw what I wanted to, and you'll see why that is tomorrow when we do geometry. There's my PCl, so that's 6 electrons used up. There are 20 left. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This time we have electrons left over, which means that we put them on the central atom. And then everything is good. All of my atoms have an octet, so this is the correct structure. What I wanted to draw for this was I actually wanted to draw it kind of like this. Oops, that's not going to work. Never mind. I don't want to waste time playing around with Photoshop trying to make it do what I want. I was going to drag stuff around. We're kind of short on time anyway, so. Uh, 20. So I'm going to do this, and you're going to see why I have it bent in just a second. So there's 4, which is 16 that are left. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And there you go. And because it's an ion, I got to do this to it. So that's our structure for ClO2-. Plenty of electrons. I did not need to make any extra bonds. And then finally for NO plus down here, 5 plus 6. But I got a plus here. That's like I took away an electron. So I have one fewer electron to work with when I have a positively charged molecule. Okay. So I'll draw the structure. There is no central atom in this case because there's only 2 atoms. So I just connect them to each other. O is the more electronegative atom, though, so I'm going to put the electrons on it first. So there's 6, 7, 8. I'm out of electrons. I got to start making double bonds now. So there we go. Still don't have an octet on nitrogen, but now I do. And I really should have just used the ones on the top and the bottom there. There we go. So there's the Lewis structure for NO+. Has a triple bond in it. All right, hopefully you did pretty good. I skipped one, didn't I? I skipped NH4. I'll just quickly draw NH4 in. All right. There you go. Good catch. I didn't even see NH4. Went straight to PCl3. But NH4 should have 8 electrons, because N is 5, each of the H's is 1, for a total of 9, and then you have a positive 1 charge, so you lose an electron to get 8. Alright, so before we go, let's talk about exceptions to the Octet Rule. When do these rules that we followed fall apart? And there are some cases where this happens. One of these cases we've already just seen. It's hydrogen. So hydrogen follows the duet rule. And the reason for that, again, is because hydrogen only has access to n equals 1 with its electrons. There's only ever 1 or 2 electrons around hydrogen to fill that n equals 1 shell. It's only got 1 proton anyway, so it can't hold on to more electrons. And so we just observe, oh, hydrogen only wants 2 electrons. That follows the duet rule, we call it. Hooray. Now, sometimes I might give you a molecule where you count up the electrons and you're like, wait a second, I got an odd number. What the heck am I supposed to do with that? And the answer is if you get an odd number, you can never satisfy the octet rule because you'll only get to 7 somewhere. So what do if you have an odd number of electrons? So the answer is you try to do the octet rule as best as you can, following the rules. And then the element that's going to get shafted is going to be the one that's the least electronegative. Because the other atoms want the electrons, and the atom that is the most positive-like is the one that just gets screwed. So in these cases, with NO and NO2 here, Nitrogen is the least electronegative atom, and so it's going to be the one that only gets 7 valence electrons instead of 8. So these molecules have unpaired electrons. Unpaired electrons are extremely reactive. And so an unpaired electron is what's known as a free radical. And you might have heard this in just like common, I don't know, out in the world, people talking about how you don't want free radicals in your body and you should have antioxidants to remove free radicals. Free radicals are bad. And people just say this word over and over without any explanation of what it means. This is what it means. Free radicals are anything that have unpaired electrons. And unpaired electrons are very reactive because this molecule has not satisfied its full S&P subshells. It needs one more electron. And so it'll react with anything else that has an extra electron. So this is a common exception is, oh, you just don't have an even number of electrons. Some elements, like lithium and beryllium, when you create ionic compounds out of them, stop at n equals 1, so they will only have a helium shell. That's pretty common, but those don't form covalent compounds, so we don't really care about them. The one weird one that's actually really special is boron. Boron is element number 5. And boron's kind of at the point where it's like, well, if I take 5 electrons, then yeah, I could get an octet, but that's kind of far away. Removing electrons would make it very ionic. Is there something that I can do? And boron just kind of decides, I'm just going to do this. Boron's pretty happy with 6 electrons for some reason. But it is also very reactive with anything that has extra electrons to donate with it. For example, this is actually chemistry that we did in my graduate laboratory. I didn't personally do this experiment. But if you replace these Fs with Hs, then that molecule was something that we made on a daily basis. And it's called an amine borane. And what this is basically saying, well, I only have 6 valence electrons here, but if I could get 2 from somewhere else, like say here, then I will react and do that. But on its own, it's fine with 6. It's just reactive in any situation that there are extra electrons around. So water could do this too. Water could form a bond to borane. Now, this also happens with inorganic compounds and metals, it turns out. So you could put ammonia on something like, say, copper. And we're actually going to do that in Chem 163. We're going to make a compound. Maybe in 162 you make the copper coordination compound. I don't know. But bonding is not necessarily just, hey, I have 2 electrons here, 1 on each atom, let's do this. I could do something like this instead to make my bond. All that we care about is that we get 2 electrons. It doesn't matter where they come from. It's more common that you'll see them where you just pair the unpaireds. But if you have an absolute dearth of electrons, you need more, and it doesn't matter where you get it, then you could share the non-bonding pairs and send them both over, and you can make a bond out of it that way. This is what's called a coordinate covalent bond. Coordinate covalent bond. Kind of outside the scope of this class. We don't really see coordinate covalent bonds very much. But they exist. So if you take Chemistry 361, then there you go. That's boron. Boron is just weird. We tend to not really work with boron that much, but if you see it on a quiz or something and you're just like, oh, what is the shape of BF3? Just remember, it only has 6 electrons around it, so it's going to make this particular triangle shape, which we will attribute in the next lecture. There are much more common exceptions. Let's see here. What about compounds that exceed the octet? That's what we're doing right now. So there are much more common exceptions for elements beyond the elements that we've been typically working with, which are like carbon, nitrogen, oxygen, and fluorine. For those elements, that are in n equals 2, this is the full valence shell. And so the maximum number of electrons that they have around them are 8. But what if I used an element that was in n equals 3? Here are all the electrons I can put in n equals 3. And that ends up being a much larger number. So for any elements that are in period 2, this is the limit. You can only have the octet rule. The octet rule works for n equals 2 elements, and it is the absolute limit. But for n equals 3, you can go beyond the octet rule. You can go up to 18. And in transition metal chemistry, 18 is the magic number. However, that being said, it is very hard to get to 18 because when we start drawing stuff around our central atom, so I'll just pick phosphorus, for example. If I had 18 electrons, that would mean I would need to coordinate 9 different things around this molecule. 4, 5, 6. Oh, that's 9. What do you know? I was just drawing lines. And it gets crowded. In fact, for this class, what we're only going to really consider is up to 6. And that's just because up to 6 things bonded is common enough. 7 does exist, and I think 8 is extremely rare, and I don't even know if 9 exists. But we're going to do up to 6, and the reason that we can go up to 6 things bonded, which would be 12 electrons, is because for elements that are in n equals 3 or higher, d orbitals are available for us to shove electrons in. Now, this only works for elements in n equals 3 or higher. We cannot do this with elements in n equals 2. Again, the reason being for n equals 2, that's my valence shell, 2s2, 2p6. I can only go up to 8. But for n equals 3, I have 18 available electrons. So I can make enough bonds to get up to 18. So that looks like this. I didn't draw the dots on this PCl5 molecule. The word that your textbook uses is hypervalent. Not super common. I only ever used it when I started teaching from this textbook. But what we're looking for, the takeaway message here is that if on this phosphorus right here, I have 2, 4, 6, 8, 10 electrons around it. That exceeds the octet rule. But because phosphorus is in period 3, which means that its valence shell, n equals 3, has d orbitals available. We could put the extra electrons for bonding into those d orbitals, and it can be accommodated. So the takeaway is, if it's n equals 2, you can only make up to 8 electrons around the atom. If it's n equals 3 or higher, and again, that means period 3 or higher, you can make more than 8 electrons worth of bonds. So what that means is that when we are looking at our molecules, look at the atom, and if it's in period 2, octet is your limit. Period 3 or higher, you can go as high as you want to, but we're only ever going to see up to 12. All right. And so this is that description in words, just in case my description didn't make much sense. It's available on the slide, so you can hit pause and watch it. I believe the last slide is to just draw these Lewis structures. We're out of time for the day. But what I want you to do is try to draw these Lewis structures, and don't worry about the octet rule, because all of the central atoms in these molecules are period 3 or higher. So what that means is, if you follow the same rules that we've been doing, which is 1, count valence electrons, 2, draw the structure or skeleton, 3, outer electrons, 4, inner electrons, 5, make double bonds. What you'll notice is that if you do something like this, if I just go F, F, F. So I'm going to just make my skeleton here. I didn't count the electrons here, so let me do this really quickly. 6 times 7 is 42, 47. So there's 48 here. $12, 18, 24, 30. So 36 were used on the outer electrons. So 48 minus 36 is 12. And then each of these bonds, 2, 4, 6, 8, 10, 12. There we go. So this would be the Lewis structure for this molecule. And you can do something similar for all of the rest of the molecules that are shown. Okay. Just follow the rules for drawing Lewis structures and you'll be all set. So go ahead and give that a shot as your sort of like homework assignment, I guess, for tonight. But that is all we have time for today. So when we return tomorrow, we're going to talk about some extra guidelines for drawing Lewis structures because you can get into some exceptions still. Talk about what resonance structures are and how they affect bonds. And then finally, we'll start working on geometry. And if we can do most of geometry tomorrow, then we're on great shape for Thursday. And then on Tuesday, we finish the class. We're all done on Tuesday. So I want to thank everybody for coming out to the lecture today. I hope everybody is able to make it for the extra lecture for tomorrow during the lab lecture and Q&A. I still will answer questions if you have them, so make sure that you bring any questions that you want answered tomorrow. And yeah, the Octet Rule is more of a guideline. A lot of this is guidelines, and really, it's just sort of, I'm going to give you molecules that always follow these rules until you get to third quarter and fourth quarter organic chemistry, and you realize, wow, molecules can just do whatever the hell they want to. But by then, you've seen enough molecules that you can start to understand why these things are happening. Anyway, that's it. Thanks for watching. Remember, exam number 2 is coming up soon. Make sure you're studying for that. Stay safe, stay healthy, stay at home.